All right, these are notes on mechanical equilibrium, movement, and vectors. So this is going to be chapter 2.4 and chapter 2.5. I'm going over this verbally so I can go straight through without questions, and you can watch it on your own time. I'll do these notes in class a little bit as well, but hopefully this helps some of you that want to move ahead or want extra practice with this. Okay, the objectives, please don't write this. Identify two types of mechanical equilibrium, calculate resultant of a vector in parallel situations, and calculate the resultant of vectors in a non-parallel situation. I'm going to describe what all of that means here in just a moment. Okay, it said, so you might want to title this, so go back. You should title this mechanical equilibrium, movement, and vectors, and then it should be set up in, shoot, took my drawing away. All right, it should be set up in Cornell note style. So again, if you're drawing across this way, you should have your title on top, and any details should go over here in this side section. Okay, and I'll try and mark things that are important. Equilibrium for moving objects. So these are the major core points of the moving objects, is the static and the dynamic equilibrium. All right, objects at rest are static, think stay, I'll go over this again, and objects moving at a constant speed in a straight line path in one direction are dynamic. So it's important to note that the state of rest is only one form of equilibrium, and if it's moving, it's a different form of equilibrium. As long as there's no net force, like there's no arrow one bigger than the other, then it's an equilibrium, and I'm going to explain what that means. If there is only one force involved, so I'm pushing something in space, that's me just pushing. There's no downward, no upward, no friction. Space has no molecules to determine, or not enough molecules to deter or cause friction. Only when there's no force at all, or when two or more forces are combined that add to zero, an object is in equilibrium. Okay, so forms of equilibrium. There's static, like this dog. There's only two forces being applied. He's not moving at all, so the only two forces are the downward force of gravity, and the upward force of the normal force. So I'm going to always refer to it as the normal force. You should also know it's support force, but in real life situations we call it the normal force. Okay, then there's dynamic equilibrium. When an object moves at a constant speed in one direction, like this dog. Constant speed, one direction. Okay, that means the gravitational force and the normal force are equal to zero, and the applied force and the frictional force are equal to zero. So that means up and down are the same, and then the amount of applied force, the amount of force the dog is putting into his movement, is just enough to counteract the frictional force. Now, if the applied force arrow was greater, then the dog would be speeding up. But because he's given just enough force to counteract the friction, this is the force of friction, then he's staying constant. He's moving at a constant speed. Okay, so here's an example. When this dude is pushing the desk, if the desk is not moving, then the frictional force, the force going that direction, is greater than the amount of force this dude is applying. Now, as soon as he gets this thing to move, not moving fast, but just sliding constantly, once it starts moving, these arrows are equal to each other. Force applied is equal to force of friction. Now you still have your force of gravity, and you still have your force of normal or support force. Okay, but it isn't until the forces are equal, applied and frictional, can this thing be moving. So like if you're trying to push on a wall or a refrigerator and it's not budging, then this thing is not moving. It's not moving. The force is greater than your applied force. Okay, the desk moves steadily. Again, frictional force is a contact force between objects that slide. So this would be a good thing to write over here. Friction. Darn it. It won't let me write it. Friction. This should be one of your terms for sure. Again, with static, you should have static and dynamic. Static, dynamic, friction. So those are all major definitions you can include in your key terms as well. So again, force of friction is equal in magnitude. I know that kind of goes against what you guys think, but the force of friction is equal to the applied force. That's what allows movement to happen. If your frictional force is greater, you're not moving that object. If it's less, then you're picking up speed, all right, because you're overcoming friction, and that gets into acceleration. Okay, here's where things get complicated. We have vectors. We already talked about vectors. Vectors show magnitude and direction. Okay, this is when we get more complicated. The diagonal of the parallelogram shows the resultant. This is a part that is going to be hard. Okay, so let's quickly review. Yes, this is review. Okay, vectors show magnitude by their size, and direction tells me this thing is going northeast in direction. And it has a decent sized magnitude because the arrow is large. This, if I drew it again, small magnitude, and it's going southwest. You don't always have to do a cardinal direction. You could just say it's going to the left or to the right, or it's going up or down. Cardinal directions are not mandatory. Okay, the sum key term here. So we should have vectors as one of our things on the side, vector. And you should have a resultant. I ran out of room. Okay, so remember, still Cornell notes. Stop jumping around. Okay, Cornell note style. Same thing I expect. I should just continue with these notes because we titled them all movement and vectors. Okay, combining the vectors are simple when they're parallel. We talked about it. They're adding and subtracting, basic math concepts. You did it with the scaffolding. If two are going to the right, you add them. They're going opposing each other. That's subtraction. 100 minus 50, 50 newtons. Show your work. I will still hold the principle that on tests and material, you'll get more points for showing your work than the right answer. Okay, here's another situation. Two are going to the right, equals 10. They're opposing each other, equals 7. They put a negative here to show you're adding them, but one's in a negative direction. Typically, if you're going left, we consider that, think about your number line. It's a negative, where if it's going right, it's positive. Just like if I put a number line up on the wall. Now, up and down, we said up is positive, down is negative. This applies with up and down as well. Okay, so here's some examples when this comes to tension. Nellie Newton, that's who we call her. She has a downward force of 300 newtons. Well, one arm going up is holding onto a rope is 300 newtons as well. That's a lot of tension. Now, they split the rope. When you add two ropes, her weight is divided among them. So it still balances out. If we had 3 ropes, it would go 100, 100, 100. We could go on and put, so the point of this is the more ropes, the more you're spreading out your weight, the more you're distributing it. Okay, we did that with the scaffolding experiment or the scaffolding demonstration. Now's where it gets harder. Okay, what if you have ropes pulling from either side? So anytime we have a right angle, we're going to apply the parallelogram rule. The resultant, we're going to just use each side, we'll call the side A and side B, to determine side C. The diagonal of this is called the resultant. So how do I solve for that? Okay, if you've done this already, it's the Pythagorean theorem. A squared plus B squared equals C squared. C will solve for your resultant. So what's A, B, and C? A is this side, and because it's a parallelogram, the sides are equal to each other, A and A on either side. The top and bottom would be B and B. They're equal. which means this is a right triangle right here. All right, this makes corresponding right triangles. Now, that results in C as your divisor of the square. This is your resultant. So now you can use B and A to solve, or sometimes they'll just give you C. You use the numbers that you have to solve for the resultant or for whatever side you have left. Okay, this requires you to set it up algebraically and move your numbers accordingly. This is the toughest part of this chapter. So let's apply all that we've learned. Nellie Newton has a frictional force going downwards, or not a frictional force, my bad, has a gravitational pull going downward, force of gravity. Okay, her force of gravity is, since she's not moving, her support force, or in this case her tension force, is equal and opposite, force of tension. But usually we draw this as a dotted line because there's no actual force. Nothing's holding her up directly up. So we use this arrow to determine what the forces are on each line. Okay? So how we do this is, notice how the tension vectors form a parallelogram. Okay? So what I drew here, so this arrow is equal and opposite to this. We are going to now draw a parallelogram. Get out a ruler and make sure it matches. So this should line up. It should make a parallelogram. See, that's not parallel. It needs to be exactly parallel, which is why I recommend getting out a ruler. Okay, I'm trying to get out a ruler for you to see. Okay. Nope, except now it went back because I touched my screen. Okay, I'm trying to draw parallel line based on what lines I have. This is the hardest part, making sure you have a parallelogram. Sorry, I keep bouncing back and forth. Then this one should be parallel. This one and this one should be parallel. This one and this one should be equal. Okay? I'm using the math symbols here. Now you can see this is where the force is going to be. This is the tensional force. You draw an arrow right there. This is terrible. I need to erase some of it for you. It won't let me erase. Okay. But that's where your arrows will go to. And this will be easier to explain in class. So I'm going to do this again here. So where she's downward, her downward force is equal and opposite to her upward force. Make sure those two arrows are equal. And then you draw a parallel line to that one and a parallel line to that one. So your corner theoretically is where this arrow hits. So I need to draw a better line. That allows you to determine that's the force on that string and that's the tension force on that string. Okay? Again, the smaller your arrows, the smaller the force. So you can see how it's kind of split here and here. It's fairly accurate drawing. Short arrow compared to a much longer arrow. Okay. So again, here's it drawn again. Equal and opposite. We use the parallelogram rule so we can determine, once we have numbers, we can figure out what the resultant will be. So, or you can determine what those are. Now, as you can see here, her force, once you get past 60 degrees, once you have like greater than 120 degrees, so greater than 120 degrees, that's when you're putting more weight. There's more weight on these outer strings. Think about it. If you tried to hold yourself up with your arms straight out, it's harder than if you just have your arms straight up. I'm demonstrating this and you can't see me. So just think about it. Put your arms out. If you had to hold yourself up again, like hold yourself up from a table, like the gymnasts on the rings at the Olympics have to do, that's a lot harder than holding yourself vertical, straight up and down. All right? So this would tend to cause a huge amount of tension. All right. Here's another when it's lopsided. Take a look at this. My time's going to run out. So think through this. This will be posted for you to take a look at. Thanks, guys.